So let us start the afternoon session. The first speaker in this afternoon is, well, Mengxue Yang.
Yes.
And she will talk about conformal limits on Cayley components.
Thank you very much to the organizers for inviting me to speak at this conference. Today I want to tell you a little bit about a correspondence between moduli spaces of Higgs bundles and flat connections on a Riemann surface that I find very interesting. And the origin of this conformal limit comes from a mathematical physics conjecture. So from physics in 2009, Gaiotto studied the superconformal field theories of class S. And in this context, led to a conjecture by Gaiotto in 2014 that certain conformal limits of TBA equations, thermodynamic Bethe-Ansatz equations, should take on the form of higher rank Schrodinger equations. That was the conjecture. So for him, he's working with a Riemann surface P1 minus 3 points, so punctured Riemann surface. And I'm not very familiar with the physical side of the story, but there is a mathematical formulation given by Dumitrescu, Fredrickson, Hidonakis, Mazel, Murase, and Knightsky in first appeared in 2016 and then published in 21 that so the mathematical formulation that they proved for this conformal limit works for a Riemann surface which is compact of genus at least 2. So not quite a punctured case, but in this case, we can formulate the conformal limit as applied to some Higgs bundles. And they show that the limit will appear as the space of opers, which is another set of mathematical objects that are very interesting in their own right. These are introduced by Billingson and Drinfeld to study geometric Lengths. And so there are no definitions so far, but I want to illustrate what a conformal limit for you in a very simple case first. So the mathematical formulation for a conformal limit when the group is SL2C. We let Q be a quadratic differential on X. And we fix a theta characteristic on X. So what are some Higgs bundles parameterized by these quadratic differentials? There are pairs of objects, a rank 2 vector bundle, so structure group SL2C, and a Higgs field. Let's call this phi Q, parameterized by the quadratic differential, where E is going to be this vector bundle, and phi takes on the form of an endomorphism valued differential. So this is taking values in I know this looks like just a local matrix, but actually this one, you can identify this as a homomorphism from k at half to k minus a half tensor by k. And so this is isomorphic to a global section of OX if you bring the k to the other side, Helm tensor junction. Okay, so that's a Higgs bundle. And on the other side, we can define a family of opers which is really a flat connection on a vector bundle. So we let E be in some way the first jet bundle on k minus a half. So if you haven't seen jet bundles before, you can view this as some sort of bundle of Taylor polynomials. So if I write kj of some bundle, this is the bundle of k jets, which may be viewed as degree k Taylor polynomials of sections of F. In other words, we can view E as a non-trivial extension of k minus a half by k positive a half. So as smooth vector bundles, these two are the same, but this one has a different holomorphic structure. And the flat connection that I put on this bundle, I'm going to call this oper, will be trivial differential plus this. And the conformal limit is supposed to relate the left-hand side to the right-hand side. In order to do that, first I need to apply a very important theorem called the non-abelian-Hodge theorem on the to the left-hand side of the Higgs bundles. So this is a well-known theorem in the theory of Higgs bundles. We know that Higgs bundles of this form are actually stable, which means that if you compute the slope of this vector bundle, which is degree over rank of the vector bundle, then phi invariant subbundles will always have strictly less slope than the slope of E phi. And such stable Higgs bundles satisfy, so by non-abelian-Hodge theorem, which you may refer to Simpson, paper in 88. There exists a Hermitian metric on E such that, oh, this is getting a little low. Maybe I'll write here. We let the H denote the turn connection associated to the Hermitian metric plus phi plus the dagger H. So the adjoints of the Higgs field with respect to the Hermitian metric is a flat connection. And I just want to remark that these Higgs bundles that I wrote down here are known as, I guess, the simplest case of a Hitchin section. And in particular, when Q is equal to 0, there's nothing here. This is an example of what I will call the uniformizing Higgs bundle. where the word uniformizing Higgs bundle comes from the fact that you can equip the bundle with the uniformizing metric, from the metric that comes from uniformizing the underlying Riemann surface. And that will solve Hitchin's equation. That will turn this connection into a flat connection for you. So now on both sides we have flat connections, and I need to show you what the conformal limit is, which will take one to the other. So the first step to the conformal limits is we will reparameterize with two parameters, zeta and a real parameter r. So the flat connection coming from the Higgs bundle will be the H, a Chern connection, plus Higgs field plus adjoints. And the first step is we will multiply this by zeta inverse and this by zeta. But this being a flat connection actually is equivalent to saying that the Hermitian metric is solving Hitchin's equation, which is this equation here. So you see, if we multiply this by zeta inverse and zeta, they can just cancel each other from this bilinear form. So this rescaling doesn't change the fact that this equation holds. The second step is we will take the Higgs field to R times the Higgs field. And it's a well-known property of the moduli space of Higgs bundles that the limit of any C star action on the Higgs field, this kind of rescaling, will end up still being in the moduli space. So this will give you another Higgs bundle, which is at least polystable, and which will give you another solution to Hitchin's equation, which depends on the parameter r. So now we fix h bar to be zeta over r, and we take r and zeta to 0. That will be the conformal limits. The statement is that as we do this, the equivalence class of flat connections coming from Higgs bundles of this form will be an equivalence class of opers. So this is a oper connection. Maybe it depends on Q and H bar. So are there any questions about this simple example? Yes. Yes, I think there's some kind of the zeta. Yeah, there is some relation. Sorry, I don't remember the correct statement off the top of my head, but yes, there should be some relationship to the. Yeah, so there is a more general form of conformal limit, which I will not explain today, but you can consider more generally the moduli space of lambda connections and study all conformal limits in that. Okay. Yes, I think that also it does give you a lambda, like an R connection, which, yeah, you can view it that way. Right. But right, yeah, I think so. So what's nice about this conformal limits is that on moduli spaces, if we let M be the stable holomorphic vector bundles on X and N double denote the stable Higgs bundles. Sorry for all the abbreviation. Maybe moduli space of stable Higgs bundles. And M the RAM denotes the moduli space of irreducible flat connections on X. Then usually we have the well-known correspondence that I mentioned earlier between M double and NDR, which is called the non-abelian Hodge correspondence. And inside M double, the moduli space of Higgs bundles, you can put the cotangent bundle of N in there, and that surge X back onto N. And here, this also holds via, the inclusion also holds via Narasimhan-Seshadri, but you can view this as a torsor over, you can view the RAM moduli space as a torsor over the moduli space of stable holomorphic vector bundles, but non-abelian Hodge doesn't commute with the rest of the arrows here. Whereas if you take the conformal limit, you don't get a continuous map on moduli spaces, but it turns out on strata of the moduli space, it gives you biholomorphisms on those strata such that this square actually commutes. So it's a different kind of correspondence between the two moduli spaces. I think you can apply Narasimhan-Seshadri to see this inclusion.
Narasimhan-Seshadri is about what about 200?
Yeah, it says that if you have you get a flat connection.
Wow.
Pointing to the cotangent fiber. I'm sorry, maybe I am, okay, so I don't remember exactly how I remember this, but it is true that you can also view this as an inclusion via the usual non-abelian Hodge. The only problem is that here there's a holomorphic structure which is not compatible with the holomorphic structure of the Riemann moduli space. So we can't view this as some sort of, like if you go this way, then it's should be a torsor instead of the usual G bundle from here. Yes, maybe let me rephrase. So the point is that this doesn't preserve the holomorphic structure, whereas this one would. Yes.
So these arrows are not most complex manifold, but diffeomorphism.
This one is a diffeomorphism. And this one is not even continuous. It is defined on strata. But you can extend it to all the points which are stable.
Is the diagram community?
With this on the strata,
Yeah,
yes.
the whole,
With this, no.
so that's just
Yeah. Sorry, this is not commutative. Yeah, sorry for that confusion. This one should be commutative. X, from my assumption at the beginning, it's a Riemann surface which is compact with genus at least 2. And let me just state some known results. From the beginning, we saw that this really long name, 21, if G is a simply connected simple complex Lie group, then the Hitchin section which I haven't defined, but as an example, is so this kind of pairs of Higgs bundles inside the bowl of G. This is a Lagrangian submanifold, goes to the space of opers, which we can view as an affine subspace, but also a space of a Lagrangian subspace inside the Riemann moduli space of flat connections. And later, this was extended on the moduli space of lambda connections, but I guess I won't state that. By the work of Collier Wentworth, first in 19, that we can extend this conformal limit to the whole moduli space. So they only considered vector bundles, SL and C. So by strata, I mean that there is a C star action on the moduli space of Higgs bundles by just scaling the Higgs field. And this give you a Bielny-Nitsky Berula stratification. On both moduli spaces, and then on these strata, the conformal limit is a biholomorphism. So at stable C star fixed points. And later, very recently, Collier Fredrickson and Wentworth extended their results to parabolic Higgs bundles. So to address Gaiotto's original conjecture on a punctured Riemann surface, they established some kind of conformal limit for parabolic Higgs bundles. But I believe their simplest example is a P1 with 4 punctures. It appears that for opers, at least, the well-defined sort of puncture needs to be an even number of punctures. So I'm not sure if they can cover 3 punctures case. Okay. So all of this is well known about the conformal limits, but recall the title of my talk is Conformal Limits on Cayley components. What are Cayley components? So the goal is to find conformal limits for Cayley components. These are components in some moduli space of Higgs bundles that are natural generalizations of the Hitchin component, or the Hitchin section. So in order to get to the generalization, first let me talk about the Hitchin component / the Hitchin section. If we fix GR to be the split real form, in some complex symbol B group. So for example, SLNR is a split real form inside SLNC. Then Hitchin in 92 showed that his vibration from the moduli space of G Higgs bundles to the Hitchin base where you take a pair of Higgs bundle and then you map phi to choose some G invariant polynomials on the Lie algebra G, choose a basis, and then you apply those invariant polynomials to phi, you get a vector inside the space. This is the Hitchin map. And this is a Hitchin vibration with generic tori fibers, and it has lots of interesting properties, but I won't talk about those here today. What is interesting for me is that in the paper 92, Hitchin constructed a section to this projection, which is called the Hitchin section. So sometimes you need to fix a theta characteristic for that. You get a section, and the image of S is some subset inside the moduli space of Higgs bundles. And once you apply non-abelian Hodge plus the Riemann-Hilbert correspondence, you will land inside representations of fundamental group valued in the split real form. So in some representation variety. And in particular, we started off with the complex group G, but if you only restrict yourself to the Hitchin section, which is the image of the section here, you will actually land in representations which are purely real. Yes? I think here I should be fine with any, like the statements here should work fine for any simple Lie group. I think just any simple Lie group up to the rank of G. And then you can take any basis of invariant polynomials for the simple, yeah. But yes, SLN would be the easiest one to consider. Maybe I didn't write, like if I need the SL, the general one, I need the, yeah, maybe possibly different degrees. Okay, sorry. So this image is a connected component. Inside the real representation variety. And moreover, it was shown by Laborie and Falk-Goncharov that in this case, the components consist entirely of discrete and faithful representations. So in the case when GR is PSL2R, you in fact get the Teichmuller space for the surface of topological type given by your Riemann surface. And that's parameterized by this Hitchin section, which is why it's called a component, because it's honestly a component in once you push through non-abelian Hodge and Riemann-Hilbert correspondence inside this real character variety. But when GR is not PSL2R, but a higher rank Lie group, then you will get connected components, which are known as higher Teichmuller spaces, which are connected components consisting entirely of discrete and faithful representations. So these are the first known examples of higher Teichmuller spaces. There are other well-known examples, which are maximal components, but more recently, Bichard and Winhard in 21, 22 proposed a theta positive structure it's intrinsic to the real simple Lie group GR. So the GRs which emit theta positive structures will give you some higher Teichmuller spaces in representation variety. But they also conjectured that they classify these theta positive structures. They conjecture that these are all the, first they classify them, and conjecture, they give all the higher Teichmuller spaces. So they definitely already give you all the known higher Teichmuller spaces. The question is, are there any more on top of that? So this is so it is the higher Teichmuller spaces that motivated the definition of Cayley components of Higgs bundles. I'm going to call this GR Higgs bundles. So first, let me give you a definition. When GR is a simple connected real Lie group, we have a global Cartan decomposition into a maximal compact subgroup and the exponential of some complement subspace in the Lie algebra. Then for notation, I will drop the superscript R to mean the complexification of an object. A GR Higgs bundle is a pair, which is a principal H bundle plus a Higgs field holomorphic H bundle, and phi is a holomorphic section of the twisted bundle. Also twisted by the canonical. And you can form a moduli space of these GR Higgs bundles. I will decorate the moduli space by a line bundle L if I replace the K by the line bundle L. So I'll twist the Higgs bundle. This is going to be the moduli space. GR. Yes. No, I just, sorry. The Ball moduli space, so I think normally this one, we put maybe the complex group here. There's no difference. I just changed the notation because this comes from, I think, Simpson's papers where he talks about the Ball moduli space, the Rem moduli space, and the Betty moduli space. But yeah, I just changed up the notation. Sorry for the confusion. Okay, let me give you a simple example. When GR is equal to SP2NR, you can decompose this into a maximal compact and exponential of the vector subspace sim n plus 2 R. So if you complexify these two objects, you will get the structure group GL and C, and you will get M is equal to just sim n plus 2C, which tells you that an SP to an R Higgs bundle should be the data of V beta gamma, where V is a holomorphic rank n vector bundle. And then you can take your SP2 and R Higgs bundle, if you like, to be V plus V dual, and that has a canonical symplectic structure on it. And your Higgs field will be of the form like so, which belongs to sim 2V plus sim 2V dual. So, yes. Theorem due to Bradlow, Collier, Garcia Prada, Gaussen, and Oliveira. In publishing 24, it appeared earlier. GR P theta R admits a theta positive structure if and only if G, being the complexification of GR, maybe I can write it like this, admits a magical triple. So I'm going to cheat in this talk. It's a little too confusing and it takes me much longer to explain what a theta positive structure is. So I will use the much simpler definition of a magical triple to characterize these Cayley components. This one is much easier to explain and it's equivalent to the theta positive structure. Just remember here, this was important because by Guichard and Winghard, they give you a conjectural classification of higher Teichmuller spaces. So what is a magical triple? We say a SL2 triple is magical, so it should also satisfy these bracket relations. It's magical if the vector space homomorphism sigma defined on G given by sending a vector x to just itself if x is in the centralizer of the triple, which I will denote by C, or -1 k plus 1 x if x is in, if you apply the lowering operator k times to the highest weight vectors with respect to the triple, except for the centralizer, the ones in the centralizer. So then this extends to a vector space homomorphism on G. And this is magical if it is actually a Lie algebra involution. That is, if it respects the Lie bracket. Are there any questions about this? So, don't have a lot of time. So I won't give you won't write down an example for you, but for example, a principal triple is magical in every Lie algebra. And for a principal triple, you can associate to a canonical real form, which is the split real form of that Lie algebra. And it turns out that in Hitchin's 92 paper, he showed that this involution associated to the principal triple, given by composing the involution that gives you the split real form with an involution that gives you a compact real form, is exactly satisfies this kind of condition with respect to the principal triple. And that shows you that the principal triple is magical. And he's able to use the principal triple to parameterize his Hitchin section. Theorem / definition. Let's G complex simple Lie group with you can associate a canonical real form to the magical triple, GR, then there exists a map between moduli spaces. So on the left-hand side, you have twisted Higgs bundles valued in some real form called the Cayley real form, which is associated to the magical triple, and some partial Hitchin base with some exponents associated to it. I don't have time to explain all of the notation, but I will give you a rough idea of why I'm writing this down. And on the right-hand side, you have the moduli space of GR Higgs bundles for that canonical real form. And here, just fix this notation for now. I don't have time to explain to you fully what this means, but sort of this GR is a simple real form, which is called of the Cayley real form, and it has some kind of Cartan decomposition given by CR exponential of some complement subspace, where CR is actually the centralizer of the magical triple inside your V group. So C is the centralizer of the magical triple. And denotes PK a half by the frame bundle of the theta characteristic. And we may write down PK a half F from the magical triple as the uniformizing Higgs bundle. So you can recall from the first example, this is just the data of the uniformizing Higgs bundle. And packaged into a language of principal bundles. Suppose psi is applying some number of times lowering operator to a vector in the highest weight space of at E. and Qi is lowering F some number of times to some vector in the highest weight space in at E, kernel of at E, then PH is defined to be PC times F times H, where C and C star actually here, C and C star commute as a subgroup inside the group H, and phi is F plus psi tilde plus the sum of Qi tildes. This is a lot of notation, but the way that I think about it is here is some kind of Cayley partner plus uniformizing Higgs bundle. And right, maybe on the bundle part. This is the Cayley partner, this is the uniformizing Higgs bundle. And then on the Higgs field, we have the lowering operator. And then we have some vectors in highest weight vectors, which is called a Slodali slice at F. And the nice thing about this map is that psi is open and closed. So the way they showed this is by computing some hypercohomology of the moduli spaces on both sides of the map and show that they coincide. And to show closeness, you just use the fact that the Hitchin map is proper. And because it's open and closed, the image of psi will be a union of connected components, and these connected components will be called the Cayley components. Of Higgs bundles. And right. Sorry, what part? This one? Here. This is a special weight associated to, I guess, this part. So you, if you're talking about the real form SLNR, it's a split real form. There is nothing here. You just get a Hitchin base. So it is only when the real form is more complicated. For example, you can talk about Hermitian Lie groups of tube type. That will give you maximal components. That will give you something non-trivial here. Or you can talk about Lie groups which are locally isomorphic to iso PQ, or some real forms that have restricted root type of F4. So there's a classification of these real forms, which is really neat. But you kind of study the real forms to get this number. There's only one that shows up in each case. Yeah. And yeah, in the case when this GR is a split real form, you just have the usual Hitchin section map. Okay, I'm a little running low on time, so I'm not going to give this example. I'll give you more example if you want afterwards. Okay, now we talked about what the Cayley components are, and we want to show that the conformal limits of these Higgs bundles are actually opers as well. And we do already expect that the opers, so we'll define the corresponding opers and then make the statements. Basically, we just check that they do match up via the conformal limits. So what are the corresponding opers? We let GR P theta R be the theta positive structure on GR. I will, or in other words, you can get some sort of parabolic subgroup from that magical SL2 triple if you like, because I haven't properly defined what this is. I'm just using this as a black box. And GR is the canonical real form associated to the magical triple.
Is it real or is it just a local?
The canonical real form. So actually, I'm sorry, what is your question?
Local. I think you have the M.Yang explained it, just people explain that is, and also that is would be associated with your canonical real form in FABC.
I can get a real form by considering involutions on the Lie algebra. So I basically take sigma and I fix some compact real form on my thing, and then I compose them. So this is from the definition of the magical, like a magical SL2 triple. I compose them. This will be the canonical. And I assume that my Lie algebra involutions integrate to the Lie group. So maybe I assume that I'm working with simply connected or adjoint type. Yeah. Okay. A G P theta offer, also due to Collier Sanders, is a triple where PG is a holomorphic G bundle. P theta is a reduction of structure group to P theta. And most importantly, we have a holomorphic connection with such that the second fundamental form relative to the reduction of structure group satisfies P. If I do this inside so this composition takes values in the orbit P theta applied to F from your magical triple. So this is actually the unique P theta open dense P theta orbit. This last condition is really important. It encapsulates both Griffith transversality and non-degeneracy if you write out all of this upper condition in terms of vector bundles. The last one will give you transversality and non-degeneracy. Okay. Finally, I can make a statement which says that, well, let PCFC be a C star fixed point in the Cayley partner moduli space. Maybe I erased that, sorry. So the Cayley map will take this to P0 to some stable fixed point in the moduli space of GR Higgs bundles. And for any parameter U in B based at P naught, so this is going to be global sections of PC twisted by some space, tensor K, and C plus 1 plus the U for Hitchin base. Some appropriate exponents, then the conformal limit of PHU in the Slodali slice, or if you like, in the Cayley component, in the image of the Cayley map, based at P naught is equal to the G P theta opers. Also parameterized by this parameter U at P naught. So to compare this with the example from the beginning, we have the uniformizing Higgs bundle is replaced by a stable C star fixed point. And the Hitchin section, so from the beginning, we have that the Hitchin base was actually a quadratic differential. We replace that by a Slodali slice. Here, this is also maybe like Hitchin base or Hitchin section. I will stop here. Thank you.
Any questions or comments?
Yes.
So suppose from the theorem you raised here like a BGOP like the theorem.
Yes.
So that suggests that non-abelian Hodge correspondence and Riemann Hibber both preserve in respect of your structure. You know that that was each section was corresponding to the real part. You were saying that also each moduli it also was in the real part, right? I mean that.
Yeah, so this is different, right? If we're just applying non-abelian Hodge, these things should land in the real representation variety. Like you apply non-abelian Hodge and you apply Riemann Hilberts. Because these are Cayley components, by definition, they sort of correspond to the real representations. Whereas these opers,
my question is maybe,
yeah.
Maybe you didn't know whether it's non-abelian Hodge or Riemann Hilbert works for weird. Does it work?
It works. I mean, you can always sort of view the real moduli space. So they are actually different moduli spaces, but you can sort of view the real one as like a covering over some fixed points in the complex moduli space. So you can I don't know, like you can view there are real points inside the moduli space of complex Higgs bundles.
Right, but does it
And
feature non-abelian Hodge?
I believe, like this correspondence or the theorem. I think it also there is a Hitchin-Kobayashi correspondence studied by Garcia Prada and his collaborator. So yes, for GR Higgs bundles, there is like you can find Hitchin solutions and get flat connections and the represent like and then apply Riemann Hilbert. It will give you real representations. So yes, there is non-abelian Hodge there.
Not a question. So you know the functions of opers or like information there that they are giving some W algebra. So can you say something about scalar components, functions thereof, like does it give some new algebra?
Oh yeah, this is not something that I have considered before, but perhaps yes, because that's the context of geometric Lagrange, I suppose, to study the algebra on opers. But yeah, I don't know the answers.
Okay. Can I ask
Yes.
a question about the? Okay, during your talk mentioned about the centralization of the centralization, and then you are the upper.
Yes.
What's the interpretation of the central chart on the standard?
Oh, so I am sorry, I'm not familiar with the physical side, physics, so I don't know about that.
But so, on the basis of this kind of quantum, technical space.
Yeah.
Can you make us a comment on quantum, technical space?
I would love to learn more about that topic, but right now I don't know.
I think that 2 years ago, Nike worked out this kind of thing.
I see. Yeah. I think in the Hitchin integrable system, so in the base case where like you have the Hitchin section and the usual oper, there is a quantization and there's some relation there. But for this one, I don't know.
Can I one more? You have in the sense of spectral network, you have just the bottom part of the Hitchin. How about the upper, bundle side? Do you have some connection between your construction to spectral network on the upper side?
So as far as I understand, the spectral networks are like studying the spectral curves and the fibers of the Hitchin vibration. So the opers, really, if we view this as the moduli space of flat connections, usually the classical case, if this is the Hitchin section, and the space of opers sit transversally, right? So I suppose that should be related to the fibers of the Hitchin vibration.
I think that you would get into you will be interested. You have the upper fiber side. You can have interpreted nice upper to central chart.
I see.
That was my question.
I see. Okay. I would love to find out more about this, but right now I don't know. Yes, thank you.
Also on that question, so along with some second question, there is also recently a question of Q opers.
Q opers. Ah, yeah.
Yeah, I wonder. I guess it is also related to this.
Yeah, I am not sure about Q opers yet. Thank you.
Well, that's